Okay, so get this, right? Imagine training these huge AI models, the ones that power, things like ChatGPT, but without needing like rooms full of these super expensive, power-hungry servers. That's the potential of DeMo. It's this brand new optimization algorithm that could totally change how we train large neural networks. We're going straight to the source, the research paper. It's called DeMo, Decoupled Momentum Optimization. It's by Bowen Pang, Jeffrey Quinnell, and Diedrich P. Kingma from New Zealand Research. And they're really trying to tackle how much computing power it takes to train these AI behemoths, especially when it comes to, language models. So our mission today is to break down DeMo, how it works, why it's such a big deal, and what it means for the future of AI.
Yeah, it really is amazing. Training these massive neural networks, the ones with trillions of parameters, it just takes a crazy amount of computing power. You need multiple top-of-the-line accelerators like GPUs or TPUs, all linked together with specialized hardware, and it's expensive.
Yeah, training these models is definitely not for the faint of heart or a small budget. But this paper suggests that there might be a more efficient way. So what's the main bottleneck they're trying to address with this DeMo?
The biggest problem is in how these accelerators communicate with each other during training. Current methods rely on constantly synchronizing information. It's called gradients and optimizer states between all of these different accelerators. It's kind of like trying to have a conversation where everyone's talking at the same time.
Oh, wow. So a recipe for disaster and probably some frustrated AI researchers. So how does DeMo propose to solve this communication problem?
DeMo, it stands for Decoupled Momentum Optimization, and it takes a completely different approach. It uses this key insight that the information needed to update the model during training, all those gradients and optimizer states, it's actually very compressible.
Compressible, like zipping a file to make it smaller, but it still has all the same information.
Exactly. DeMo finds a way to, zip that information that they're exchanging, making communication much more efficient. And it's based on three main ideas. The researchers call them conjectures.
Conjectures. Okay, I like it. What are these core principles behind DeMo?
So the first conjecture is that the parts of the momentum that change quickly, and you can think of momentum like the optimization process as memory, that these are highly spatially correlated. So it's kind of like patterns that are repeating across the data.
So there's like a redundant information being shared.
Yeah, and DeMo takes advantage of that redundancy. The second conjecture says that these fast-changing components, they need to be applied immediately, whereas the slower-changing components, they can be averaged over time.
Oh, that makes sense. Don't want to get bogged down when there's important information to deal with.
Exactly. And the third and probably most important conjecture is that these slower changing components, even though they change slowly, they're really important for the model's long-term performance.
So it's about finding a balance between speed and long-term learning.
Interesting. But how does DeMo actually do this compression?
It uses this trick from signal processing called the Discrete Cosine Transform, or DCT. You probably use it every day without realizing it. It's used for image and audio compression.
Wait, so the same tech that shrinks my music files is being used to train these giant AI models. That's pretty cool.
Yeah, it is. So DeMo uses DCT to extract these essential frequency components from the momentum, which is like finding the most important signals in all that data. Then it compresses them a lot. And only these compressed components are synchronized between the accelerators. And this reduces the communication overhead by quite a bit.
So instead of sending the entire, meeting transcript, they're just sending the bullet points.
Yeah, that's a perfect way to put it. They even have this variant of DeMo called Signum DeMo, which simplifies things even further and uses even less memory. So it's super efficient. Oh, wow. So they found a way to make it even leaner. Impressive. But does it actually work in practice?
That's the exciting part. They tested DeMo using a standard language model. It's called OMO, and it was trained on this massive data set called DOLMA.
Okay, I'm on the edge of my seat. Did DeMo deliver?
Yeah, the results were really impressive. DeMo either matched or even beat the standard AdamW optimizer, but with way less communication between the accelerators. Think about it. It got similar or even better results while drastically reducing, how much data was being sent back and forth.
So they're getting more out of their computing power. That's huge, especially for, researchers that don't have unlimited resources.
Exactly. And here's the really cool part. They did this using the same learning rate and hyperparameters as AdamW. So that means DeMo could be integrated into existing AI development without a lot of, fiddling around.
That's like true plug and play. No complicated setup, just better efficiency right away. That's pretty amazing. But before we get too carried away, I'm kind of curious about how this DCT thing actually works. It sounds kind of complicated, like straight out of a textbook.
It might sound complex, but the basic idea is actually pretty simple. Imagine you have a detailed image, like a photograph. You can represent that image in terms of its different frequencies. Some frequencies capture the big shapes and the overall structure, while others represent the fine details and textures.
Okay, I think I get that. So it's like breaking a picture down into its building blocks.
Exactly. And the DCT is just this mathematical tool that lets you separate out those different frequencies. And the really interesting part is that most of the important information in an image, it's often concentrated in just a few of those frequencies.
So you're saying that the essence of a picture can be captured by its main features and not, every single pixel.
Exactly. And that's where the compression comes in. By focusing on just those dominant frequencies and getting rid of the less important ones, you can represent the image with much less data without losing too much information.
It's like writing a summary of the image, but with frequencies instead of words.
Precisely. And we can do the same thing with the momentum in neural network training. Instead of a picture, we have all these numbers representing the momentum, which is changing all the time during training. DeMo uses DCT to analyze those changes, and it extracts the most important frequencies that are driving the optimization.
So instead of synchronizing every single number between the accelerators, they're just focusing on the key frequencies.
Exactly. This dramatically reduces the amount of data that needs to be communicated, and it makes the whole training process, much more efficient.
That's a really clever way to make things faster.
Yeah.
I'm starting to see why these researchers are so excited about this. But did they only test this on language models? Or did they try it on, other types of AI?
They actually tested DeMo with a smaller model, too. It had 300 million parameters, and they saw similar results. This suggests that DeMo's efficiency gains, they aren't just limited to those huge language models, but could be used for a lot of different AI applications.
That's really interesting. It seems like DeMo could go way beyond just language models. So what does this mean for the future of AI? Could this be the key to, even more powerful AI?
It definitely has the potential to change things. Imagine training models with trillions or even quadrillions of parameters.
Yeah.
Models that could understand and generate language with incredible accuracy.
That's pretty mind-blowing. But of course, with great power comes great responsibility. What are the potential downsides of DeMo? It almost seems too good to be true.
Well, it's important to remember that no technology is perfect. While DeMo's results are, really exciting, there are still some things to keep in mind. For example, fine-tuning the hyperparameters. You can think of those as the controls for how DeMo works. That'll be important for getting the best performance with different models and data sets.
So it's not like, set it and forget it. There's still some work to do to get the most out of DeMo.
Yeah, exactly. It's not a one-size-fits-all solution just yet. But that's also what makes this research so interesting. This is really just, the beginning for DeMo. As more researchers start using it and experiment, we'll get a much better understanding of, what it can do and what its limitations are. And who knows, we might even see new versions and improvements as people, explore its potential.
It's like giving AI researchers a whole new toolbox, with DeMo being the shiny new hammer everyone wants to try out. Speaking of tools, the researchers actually made their PyTorch implementation of DeMo available on GitHub. That's a big deal for open source, right?
Absolutely. Making the count open source is, a great way to encourage collaboration. It lets researchers from all over the world jump in, experiment with DeMo, build upon it, and maybe even discover new uses for it that we haven't even thought of yet.
That's the great thing about open source. Everyone benefits. Okay, so we talked about the technical stuff.
Yeah.
And how DeMo could make AI training faster. But I think it's also important to step back and look at the big picture. What does it mean to be able to train these massive AI models? It's kind of a double-edged sword, isn't it?
It is. On the one hand, the potential benefits are huge. Imagine AI that can help us solve some of the world's, toughest problems. Things like climate change, disease, poverty. AI that could personalize education, make healthcare more accessible, and even, create new forms of art and entertainment.
Those are some really inspiring possibilities. But of course, there's the other side of the coin. What about the risks? We've all seen those sci-fi movies where AI becomes too powerful and things go, really wrong.
Those concerns are definitely valid. Like with any powerful technology, we need to be careful and responsible about how we develop and use AI. We need to think about the ethical implications, ensure fairness and transparency, and put safeguards in place to prevent misuse. This isn't just a technical problem. It's a societal one. It requires, collaboration between researchers, policymakers, and the public.
It's a huge responsibility, but one we can't ignore. The future of AI really depends on, on how we deal with these challenges.
That's right. It's like we're at the beginning of a new frontier. We have this incredibly powerful tool, but how we use it will decide, what happens next.
That's something to think about. It seems like DeMo isn't just, changing AI training. It's making us think about some big questions about AI in our future. So for everyone out there exploring AI, keep those questions in mind. The answers will shape the world we live in.
Yeah, the journey is just beginning.
Well, it's another deep dive done. Today we explored DeMo. It's this potentially game-changing algorithm that's pushing the limits of AI. As always, thanks for joining us on this journey of knowledge. Until next time, keep those brains buzzing.